Any carbon compounds which contain COOH as a functional group will be considered as carboxylic acids. Number of carboxyl acids are going to increase, then it will be indicated by di-tri before oic acid. The carboxylic acids will be prepared through esters, amides, nitriles, alcohols, aldehydes. Hello everyone, this is Harshita Bhavasar from Vidhyaashram PU College Temple of Excellence. Now I am going to start session 4 from the chapter Aldehydes, Ketones and Carboxylic acids. In the last class we have discussed about some of the chemical properties of ketones, oxidation of methyl ketone, reactions due to alpha hydrogen, aldol condensation, cross aldol condensation, Cannizaro's reaction, electrophilic substitution reaction and uses of aldehydes and ketones. These are the concepts which we have discussed already in previous session. In the current session, we will discuss about the third part of this unit, that is carboxylic acids, its nomenclature, structure of carboxyl group, methods of preparation of carboxylic acid and physical and chemical properties of it. Carbon compounds containing a carboxyl function group, that is COOH, are called carboxylic acids. Any carbon compounds which contain COOH as a functional group will be considered as carboxylic acids. The carboxylic group consists of carbonyl group attached to a hydroxyl group, hence its name is carboxyl. Means carbonyl group attached to hydroxyl group. For CO, OH is added, that's why we will call it as carboxyl. Note, some higher members of aliphatic carboxylic acids, that is C12 to C18, known as fatty acids, occur in natural fats as esters of glycerol. Means higher members of aliphatic carboxylic acids are like C12 to C18 will be considered as fatty acids and natural fats as esters of glycerol. This is the total definition and introduction part for carboxylic acids. Next, nomenclature. In the IUPAC system, aliphatic carboxylic acids are named as follows. By replacing the ending E in the name of the corresponding alkane with oic acid. With oic acid means if it is methane is present, last E will be removed and it will be added with oic acid. So, methanoic acid or propanoic acid, like that. Okay. Carboxylic carbon is numbered 1. If more than one carboxyl groups are present, then the ending E of the alkane is retained. More than one carboxylic acid is present. If it is present, then E will be remained. The number of carboxyl groups is indicated by adding prefix di, tri, etc. to the term oic acid. If number of carboxyl acids are going to increase, then it will be indicated by di, tri before oic acid. The given table lists the common and IUPAC names and structures of some carboxylic acids. See here, this is formic acid in common name and this is methanoic acid, acetic acid, ethanoic acid, propanoic acid because 3 carbon and this is propanoic acid, butyric acid, this is butanoic acid, isobutyric acid, this is 2-methyl propanoic acid and this is oxalic acid, COOH and COOH, this is ethane dioic acid and here malanoic acid and this is propane dioic acid. We have told that more than one carboxylic acid is there, this E will be retained before di and oic acid. This is succinic acid, here butane dioic acid and this is glutaric acid and pentane dioic acid. Okay, this is how the names and structures of some carboxylic acids. You have to know some of the common names also and IUPAC names also. Next, structure of carboxyl group. Carboxyl carbon is less electrophilic than carbonyl carbon because of resonance. Okay, carboxyl carbon is less electrophilic. Less electrophilic means it has less power of the gaining of electrons. So comparative to carbonyl and carboxyl group is less electrophilic than carbonyl carbon because of resonance. Okay. Bonds to the carboxyl group lie in the plane and they separated by 120 degree. Here also all the bonds are present on the plane and it will be separated by 120 degree. Okay. Here double bond will be shifted towards here and it will become positive sign, it will be negative. Here it is already having more electrons towards oxygen and it will be given out to carbon and it will become positive, and here it will be tetravalent and oxygen already it is more in electrons. Next, methods of preparation of carboxylic acid from primary alcohols. How the carboxylic acids will be prepared from primary alcohols. Primary alcohols are oxidized to carboxylic acids when treated with potassium permanganate. Potassium permanganate we know already it is a good oxidizing agent. Primary alcohols when oxidized through alkaline KMnO4 in neutral or acidic or alkaline media, or potassium dichromate in potassium dichromate and chromium trioxides in acidic media, it forms carboxylic acid. We know potassium permanganate or potassium dichromate are the best oxidizing agents. They may be used in, potassium permanganate may be used in neutral, acidic or alkaline medium, but potassium dichromate should be used in acidic medium. That's why the primary alcohols will converted into or will get oxidized to form carboxylic acid. Okay, see here, this is decanoic acid through the alcohols. Next, from alkyl benzenes. Aromatic carboxylic acids can be prepared by vigorous oxidation of alkyl benzenes with chromic acid or acidic or alkaline potassium permanganate. The entire side chain is oxidized to the carboxyl group irrespective of length of the side chain. Aromatic carboxylic acid can be prepared by vigorous oxidation of alkyl benzene. This is alkyl benzene, and in the presence of oxidizing agent, that is potassium permanganate in alkaline medium, that is potassium hydroxide medium, it will form one intermediate and get hydrolyzed to form benzoic acid. Here also alkyl benzene with same parameters, potassium permanganate in alkaline medium, and here it will form benzoic acid, and further hydrolysis it will form benzoic acid. Okay. Next, from nitriles and amides. Nitriles are hydrolyzed to form amides and then to acids in the presence of H or OH minus as catalyst. Nitriles in acidic or basic medium it forms amides. Okay, RCONH2 which is a amide, and next in the presence of acid or basic medium it will form carboxylic acid. This is ethanamide and ethanoic acid will be formed. From benzamide, benzoic acid will be formed. The corresponding acids will be formed through which amide we have used. Next, from Grignard reagent. Grignard reagent we know already, RMgX. Grignard reagents are react with carbon dioxide which is a dry ice to form salts of carboxylic acids, which in turn give corresponding carboxylic acids after acidification with mineral acid. This is Grignard reagent with dry ice, that is CO2, and in the presence of dry ether it will form one intermediate, and on hydrolysis or acidification it will form carboxylic acid. Okay. Here also Grignard reagent for R place CH3, for halogen place Br, reacting with CO2 in the presence of dry ether, intermediate on acidification acetic acid will be formed. Next, from acyl halides. Acid chlorides when hydrolyzed with water. Acid chlorides when hydrolyzed with water give carboxylic acids or more readily hydrolyzed with aqueous base to give carboxylate ions, which on acidification provide corresponding carboxylic acid. This is acid chlorides. With hydrolysis also it may form carboxylic acid, or in the basic medium or aqueous base medium. In the acidic medium, it will form carboxylic acid. And this is from acyl anhydrides. Anhydrides are hydrolyzed to corresponding acid with water. This is benzoic anhydride. In the presence of water or get hydrolyzed with water, it will form benzoic acid. This is benzoic anhydride and this is from benzoic acid plus ethanoic acid. Okay. Next, from esters, acidic hydrolysis of esters gives directly carboxylic acids, while basic hydrolysis gives carboxylates, which on acidification give corresponding carboxylic acids. If we do hydrolysis through acid, it will form benzoic acid or carboxylic acid directly. If we use in the basic medium, it will form carboxylate ions or carboxylates. Later, it will form on the hydrolysis, it will form carboxylic acid. Okay. If we use acidic medium, directly converted into carboxylic acid. If we use in the basic medium, it will form carboxylates, then hydrolyzed. Later, it will form carboxylic acids. These are the methods in which the carboxylic acids will be prepared through esters, amides, nitriles, alcohols, aldehydes like that, etc. Now, we will see the physical properties of carboxylic acid. Aliphatic carboxylic acids up to 9 carbon atoms are colorless liquids at room temperature with unpleasant carbons. Carboxylic acid till 9 carbons means C9 should be there. Till that unpleasant odor will be present in that members. The higher acids are wax-like solids and are practically odorless due to their low volatility. Means after C9 or higher carboxylic acids, it will be wax-like in nature and they are odorless because the volatility of the carboxylic acid will be less. Carboxylic acids are higher boiling liquids than aldehydes and ketones, even alcohols of comparable molecular masses. It has higher boiling point than aldehydes and ketones because of molecular masses. This is due to more extensive association of carboxylic acid molecules through intermolecular hydrogen bonding. Why it is having higher boiling point means there is a formation of hydrogen bonding. Hydrogen bonding. The hydrogen bonds are not broken completely even in the vapor phase. In fact, most carboxylic acid exist as dimer in the vapor phase or in the aprotic solvents. It will form hydrogen bond, intermolecular hydrogen bond, and the hydrogen bonds will not broken completely in the vapor phase also. And most carboxylic acid exist as dimer in the vapor phase or in the aprotic solvents. It will present as a dimers. So, it will not break. Simple aliphatic carboxylic acids having up to 4 carbon atoms are miscible in water due to the formation of hydrogen bonds with water. Till C4 carbon atoms in the carboxylic acid, it will miscible in water due to the formation of hydrogen bond with water. Higher carboxylic acids are practically insoluble in water. Due to the increased hydrophobic interaction of hydrocarbon part, benzoic acid, the simplest aromatic carboxylic acid, is nearly insoluble in cold water. Carboxylic acids are also soluble in less polar organic solvents like benzene, ether, alcohol, chloroform, etc. This is about physical properties of carboxylic acids. Next, chemical properties. Reactions involving cleavage of OH bond. Cleavage of OH bond means oxygen and hydrogen bond should be cleaved. For the cleavage of OH bond, what are the reactions will be involved? We will see in the chemical properties list. First one, acidity. The carboxylic acids evolve hydrogen with the electropositive metals and form salts with alkalis. Okay, they evolve hydrogen gas when the carboxylic acid reacted with electropositive metals and they will form salts with bases. This is acid reacted with metal, it will form sodium carboxylate with the liberation of hydrogen gas. This is acid reacting with base, it will form salts and water liberation. This is also base, formation of salt with water plus carbon dioxide. This is overall sodium bicarbonate. Okay. Carboxylic acid dissociate in the water to give resonance stabilized carboxylate anions and hydronium ions. Carboxylic acid, when treated with water, it will dissociate into stabilized carboxylate anions and hydronium ions. Okay. For the above reaction, equilibrium constant will be concentration of product by concentration of reactant. If you want to find out the concentration of water, product by reactant will be there. Here KEQ is the equilibrium constant and Ka is the acid dissociation constant. For convenience, the strength of an acid is generally indicated by pKa value rather than Ka value. pKa will be equal to minus log Ka. Smaller the pKa, the stronger the acid. Strong acids have pKa value lesser than 1. Moderately strong acids have pKa values between 1 and 5. Weak acids have pKa value between 5 and 15. Extremely weak acids have pKa values greater than 15. Okay. So, you should aware of this pKa values. Carboxylic acids are amongst the most acidic organic compounds. These are the most acidic organic compounds and you should aware of these points to analyze about the strong and weak acids. Carboxylic acids have higher acidity compared to phenols because the negative charge in the carboxylate ion is delocalized over 2 electronegative oxygen atoms, whereas it is less effectively delocalized in phenoxide ion between 1 oxygen and less electronegative carbon atom. If you compare phenols and carboxylic acid in the carboxylic acid, carboxylate ion will be delocalized between 2 electronegative oxygen, but in the phenoxide ion between 1 oxygen and less electronegative atom will be less delocalized. Thus, the carboxylate ion is more stabilized than phenoxide ion. So, carboxylic acids are more acidic than phenols. So, due to the more delocalization in the carboxylate ion, it is more stabilized. That's why it is more acidic than phenols. Next, effects of substituents on the acidity of carboxylic acids. Electron withdrawing groups increases the acidity of carboxylic acids by stabilizing the conjugate base through delocalization of the negative charge by inductive and resonance effect. It is having electron withdrawing group, that's why stabilizes the carboxylate anion and strengthens the acid, and in this group electron donating group destabilizes the carboxylate anion and weakens the acid. If you have EWG, that is electron withdrawing group, it will enhances the strength of the acid. The order of the effect of groups in increasing acidity, first will be CF3 in the highest side, phenols only the least side. Okay. Thus, the following acids are arranged in order of decreasing acidity based on pKa values. As we have told, pKa value is more means it is less acidic. Okay. You can see here with the examples and it will continue more. CF3 will be first, pH will be last. Direct attachment of groups such as phenyl or vinyl to the carboxylic acid increases the acidity of corresponding carboxylic acid due to resonance effect shown below. Due to the phenyl or vinyl groups attaching, it will have acidity more, acidic nature will be more because of resonance effect. Okay. This is because of greater electronegativity of sp2 hybridized carbon to which carboxyl group is attached. The presence of electron withdrawing group on the phenyl of aromatic carboxylic acid increases their acidity, while electron withdrawing group decreases the acidity. Okay. We know that if carboxylic acid having electron withdrawing group, then increases the acidity. If it is having electron withdrawing group attached to it, it will decreases the acidity. Okay. It is electron withdrawing group So methoxy here, pK value is 4.46. This is nitrobenzene, it is donating group. That's why it is having pK value less. Reactions involving cleavage of COH bond. Carbon and one side oxygen and hydrogen bond is present, another side carbon. To cleave that bond, what are the reactions involved? Formation of anhydride. Carboxylic acids on heating with mineral acids such as H2SO4 or with P2O5 give corresponding anhydride. This is ethanoic acid. Treating with P2O5 and it will form ethanoic anhydride. Okay. Esterification. Carboxylic acids are esterified with alcohols or phenols in the presence of a mineral acid such as concentrated H2SO4 or HCl gas as a catalyst. This is acid, this is alcohol. It will be get esterified when the mineral acid has been act as catalyst. Then esters will be formed. Reactions with phosphorus pentachloride, phosphorus trichloride and SOCl2. The hydroxyl group of carboxylic acid is replaced by chlorine atom when treated with PCl5, PCl3 and SOCl2. That is thionyl chloride. Thionyl chloride is preferred because the other two products are gaseous and escape the reaction mixture, making the purification of the products easier. Okay. Here acid, when PCl5, RCOCl plus PCl3 plus HCl will form. With PCl3, RCOCl, H3PO3, that is phosphorus acid, and here with thionyl chloride, sulfur dioxide and HCl will be formed. Reactions with ammonia. Carboxylic acids react with ammonia to give ammonium salt, which on further heating at higher temperature give amides. Okay. Acid treating with ammonia, ammonium acetate, that is a salt, will form. On giving more temperature, water will be removed, acetamide will form. This is ammonium benzoate, benzoic acid treating with ammonia, ammonium benzoate, this is benzamide. This is another example, phthalimide will be formed through ammonium phthalate and benzoic acid. Reduction. Carboxylic acids are reduced to primary alcohols by lithium aluminium hydride or better with diborane. Diborane does not easily reduce functional groups such as ester, nitro, halo, etc. Sodium borohydride does not reduce the carboxylic group. Usually, carboxylic acid, by using reducing agents, lithium aluminium hydride, it will reduce to alcohol, but you can use borane also, diborane also, ether also, but preferably you cannot use diborane because it will not reduce functional groups such as ester, nitro, halo, etc. But in this only you can use diborane or lithium aluminium hydride. Next, decarboxylation. Carboxylic acid lose carbon dioxide to form hydrocarbons when their sodium salts are heated with soda lime. The reaction is called decarboxylation. Here, decarboxylation means carbon dioxide will be removed in the presence of base and calcium oxide. RH will be present plus sodium carbonate. This will call it as coal-based electrolysis. On electrolysis of an aqueous salt of alkali metal salts of carboxylic acids, the salts undergo decarboxylation, forming hydrocarbons containing twice the number of carbon atoms present in the alkyl group of the acid. This is about coal-based electrolysis. But here you have to observe the carbon dioxide will be removed and RH will be formed with sodium carbonate liberation. This is the hydrocarbon where in this reaction only it will form. Next, substitution reactions in the hydrocarbon part. Halogenation. Carboxylic acids having alpha hydrogen are halogenated at the alpha position on treatment with chlorine or bromine in the presence of small amount of red phosphorus to give alpha halocarboxylic acid. You know, here also having alpha hydrogen in the alpha position only, halogens will be added to form alpha halocarboxylic acids. Okay, and in the red phosphorus will be used. See here, in the alpha carbon only halogen will be used. Halogen means chlorine or bromine will be attached. That is called halogenation, or Hell-Ollard-Zelinsky reaction will be called. Next, ring substitution. Aromatic carboxylic acids undergo electrophilic substitution reactions in which the carboxylic group acts as a deactivating and meta-directing group. They do not undergo Friedel-Crafts reaction because the carboxyl group is deactivating and the catalyst aluminium chloride gets bonded to the carboxyl group. Here, aromatic carboxylic acid will undergo electrophilic substitution group or meta-directing group because it is a deactivating group. Okay. Here nitrating mixture if you use meta-nitrobenzoic acid will be formed. If bromine or ferric bromide is used means meta-bromo-benzoic acid will be used. Next, uses of carboxylic acids. Methanoic acid in rubber, textile, dyeing, leather and electroplating industries. Ethanoic acid as a solvent or a vinegar in a food industry. Hexanoic acid in the manufacture of nylon 66, that is a polymer, textile industry. Higher fatty acids for the manufacture of soaps or detergents. Esters of benzoic acid in the perfume industry. Sodium benzoate as a food preservative. Usually this acid, carboxylic acid, it will be used commercially for a wide range of industries. This is about overall concept of carboxylic acid, its introduction, nomenclature, nature of COOH bond, also methods of preparation and its reactions and uses. So this completes your chapter Aldehydes, Ketones and Carboxylic acid. I hope you have completely understood whatever I have taught in this lesson. So we'll meet in the upcoming lesson. Till that, thank you.